Hello everyone. As a conclusion to the Riemann sums section, we're going to discuss in this video the fundamental theorem of calculus. In previous videos, we have introduced the definite integral and how it relates to the limit of Riemann sums. If you recall, the limit as n goes to infinity of the sum of f of xk delta x was a way to represent the process where rectangles were built within the interval a to b between the x-axis and a function that was continuous called f of x. The limit process reduced the size of the rectangles to eliminate any estimation errors. Eventually, we introduced the idea of the definite integral, or at least the notation with the elongated s symbol. So integral from a to b, f of x dx, f of x being the integrand. At this point, the only thing that differentiated these two elements was the notation, because both were actually representations of one same thing, the net area between a continuous function and the x-axis. You will most likely agree that using the limit of Riemann sums to compute net area was relatively tedious in the past. In this video, we're going to discover how notions from Cal 1 can be linked to the definite integral in a way that we actually can save time. Although we will not prove the fundamental theorem of calculus, the following example may convince you to take a leap of faith and accept it as it is. For example, find the net area that is bounded between the function 3x squared plus 6x and the x-axis within the interval 0 to b using the limit of Riemann sums. You'll see in a moment why I've chosen to give the right-hand bound an arbitrary name, b in this case. One thing is clear, this is a parabola that will remain above the x-axis, and that is clearly continuous. In other words, in this example, we are going to compute the definite integral from 0 to b, 3x squared plus 6x dx. Since we don't know any better, for now, we're going to use the same process we have used in the past, which is to go through our step-by-step procedure. The width of each of the subintervals, or the base of each of the rectangles, is obtained by doing b minus 0 over n. So b over n. The right-hand point of each of the subintervals is obtained by adding a plus k delta x. So in this case, a is 0, and therefore 0 plus k times b over n is b over n times k. Those would be the right-hand points of the kth rectangles, or the kth subintervals. Applying this expression for xk to the function we are dealing with, the function being 3x squared plus 6x, calculated at xk will reveal 3xk squared plus 6xk, and replacing xk by what it stands for, which is b over n times k, then the function's value at xk is 3b squared over n squared times k squared plus 6b over n times k. Looking past or beyond all of this algebra, always keep in mind these are the heights of rectangles calculated above the right-hand points of each of the subintervals. Delta x equal b over n is the width of those rectangles. So according to Riemann sums, we can find the net area by adding the function's heights, or if you prefer the rectangle's heights, times their width. I've distributed delta x, b over n, to both terms of the summation, and using properties, we can split the sum of these added terms into two summations, after which we can even extract all terms that do not involve k's, treating them therefore as constants. Here's where things get interesting. We have highlighted in red the summation formulas for k squared and k, for which we luckily have rules and formulas that will provide us with the actual total that these summations produce. In the case of the sum of k squared, n plus 1, 2n plus 1 over 6 is the total value of that summation. In the case of the sum of k, n plus 1 over 2. As we've done in the past, one way to simplify this expression is to regroup numbers with numbers. So in the first fraction, 3 over 6 is a half. In the second, 6 over 2 is 3, so the numbers were simplified. And the n cubed and n squared dividers were distributed to each term of the numerators that were presented in each fraction. This allows us to cancel off the n over n fractions and to divide term by term the n plus 1, 2n plus 1 terms that appear. So here is a simplified version of our Riemann sum. B cubed over 2 times 1 plus 1 over n times 2 over n plus n, and 3b squared times 1 plus 1 over n. This is still the estimated net area because we haven't yet conducted the limit of the Riemann sum, and that'll be our next step. So the actual limit that takes place when n is brought to infinity reduces our expression to b cubed plus 3b squared. So in other words, the entire result of our definite integral, which we calculated through a Riemann sum, from 0 to b, 3x squared plus 6x, is equal to b cubed plus 3b squared. So I'm wondering, do you notice anything about the result, 3b cubed plus 3b squared, and how it relates to the function whose net area was being calculated, which is 3x squared plus 6x? So is that link even possible to find? Well, let's pretend that we were to create a function, and I'm going to call it big F, calculated at b, whose result is equal to b cubed plus 3b squared. This result would actually come from a function calculated at x, whose expression would be x cubed plus 3x squared. Perhaps this is easier a function to use to establish the link now between the integrand and x cubed plus 3x squared. Perhaps you've noticed that the derivative of x cubed plus 3x squared is in fact 3x squared plus 6x, which was the original integrand. So that was the function f of x appearing in our integral. So the derivative of big F equals x cubed plus 3x squared is little f, 3x squared plus 6x. Likewise, from now on, we'll tend to say that x cubed plus 3x squared is an antiderivative of f of x equals 3x squared plus 6x. Why the incorporation of this new word? Well, it's because of the order. In Cal 1, we were given a function and we were differentiating it to find eventually its slope. In the example we just did, it looks like in order to find or to solve the definite integral, we need to undo or find an antiderivative of the function that was acting as the integrand. So in one direction, we were finding the derivative. So this was what was done in Cal 1. And this time it looks like it would be useful for us to find the antiderivative. So the function whose derivative would have produced 3x squared plus 6x. Now keep in mind that if we had added an arbitrary constant to big F, this would still work. The derivative of x cubed plus 3x squared plus constant would still be 3x squared plus 6x, which means that x cubed plus 3x squared plus k is also an antiderivative of 3x squared plus 6x. So differentiating produces only one answer, but anti-differentiating has multiple answers that are different depending on the constant that we pick. So here's a new definition for us. Big F of x is an antiderivative of little f of x if big F prime is equal to little f. But wait, sir, does that mean that when we integrate 3x squared plus 6x, both answers are correct? In other words, could I also have said that the answer is b cubed plus 3b squared plus k? Well, actually, that would not make sense. Because remember how the definite integral represents net area. There should only be one answer for that. One could presume, referring to our previous example, that if the net area between 0 and b of 3x squared plus 6x dx is b cubed plus 3b squared, then if we had done the definite integral from 0 to a similar answer would have been obtained, which is a cubed plus 3a squared. You can go through the algebra and convince yourself this would be the outcome as well, but basically every b would have been converted into a's as well. So if you remember from the additive interval property, integrating from a to b could be replaced by the integral from a to 0, followed by the integral from 0 to b. This property is true whether 0 is between a and b or not. The first integral, a to 0, unfortunately, does not have the bounds in the order we would wish for them to have. So if we flip the order from a to 0 to 0 to a, we also have, using a property seen previously, to switch the sign of the answer. Luckily, we know the results for both of these definite integrals. So in the first one, minus a cubed plus 3a squared. In the second, b cubed minus plus 3b squared. In the last row, I've switched the order. So b cubed plus 3b squared minus a cubed plus 3a squared. Do you notice that even if we had added k values to each of these antiderivatives, calculated at b and at a respectively, the k's would cancel. So here is the fundamental theorem of calculus. Let little f represent a continuous function over the interval a to b, and let big F of x represent any antiderivative of little f. Then the definite integral from a to b of f of x dx is obtained from the difference f at b minus f at a. Between these two extremities, I've incorporated some notation that is typically used. So big F of x is an antiderivative of little f. The vertical line with the bounds a and b simply indicate that this function is to be calculated at b and at a respectively. For example, if we wanted to compute the definite integral from 0 to pi over 2 cos of x dx, according to the fundamental theorem of calculus, we would have to find, first of all, an antiderivative for cos. So from count 1, we actually know that big F of x equals sine of x is an antiderivative of cos, since the derivative of sine is cos. According to the fundamental theorem of calculus, that means that using the sine function, calculating it at pi over 2, at 0, and finding their difference will be enough to solve this definite integral. Sine at pi over 2 minus sine at 0 will equal 1. Note that we also understand that sine of x plus 5 is an antiderivative of cos of x, because the derivative of sine of x plus 5 is equal to cos of x as well. So the fundamental theorem would allow you to use sine of x plus 5 as an antiderivative, calculated at pi over 2 and at 0, and finding their difference will still give a result of 1.